Okay, for octal and hexadecimal now, remember I mentioned that they are ways to let us humans better interpret binary codes. Now the beauty of octal and hexadecimal is they are multiples of 2, octal being 8, hexadecimal being 16, which are both multiples or powers of 2. So it's very easy to convert binary numbers into this number system. So let's take an example binary number. I'm just going to pick a random one. All right, let's see, 10110111. Okay, now, how many 2's are there in the number 8? Well, there are 3 2's. 2 to the 3 equals 8. So if we group 3 binary digits or bits together, we will get 1 octal digit. So 3 bits gives us 1 octal digit. Remember, in octal we have the digits available to us of 0 to 7. So if we group these into groups of 3, and you can always add leading zeros because they don't add any magnitude to the value of the number, we can get our octal digits. So here we have 111, and if you recall from the previous video, this would be 1 plus 2 plus 4, so this is 7. And then we have 110, that's going to be no ones, 2 plus 4, so that's a 6. And then we have 1, 2, 4, we have a 2. So the number 010110111 in base 2 or radix 2 is equal to 267 in base 8. Now here you see it's very important to specify the radix because this could also look like a decimal number. So you need to make sure that you know this is in base 8. Now we can do something very similar with hexadecimal. Now let me just write out what hexadecimal is. How many binary digits or bits do we need for one hexadecimal digit? Well, remember, same thing that we did with octal, we figured out how many 2's fit into 16. So 2 to the 4 equals 16. So we have 4 bits. It's bad writing up there. 4 bits is going to give us 1 hexadecimal digit. All right, so let's first look at all of our hexadecimal digits. We need 4 bits to represent one of them. So the first one we have is a 0. This is our 0 in hex. Then we have a 1. This is a 1, a 2, a 3, and a 4, a 5, and a 6, a 7, and 8, and 9, and 10. Now instead of writing 10, we're going to use the letter A. Then we have 11, which is B, 12, oops, it's a 1, sorry, 1, C, 13, which is D, 14, which is E, and 15, which is F. Now this, once again, is another thing that electrical and computer engineers should memorize, or you will, just by the fact of you're going to be taking all these courses and using these over and over again. So you would know that if you see this group of 4 numbers, 1100, you're going to get a hexadecimal digit of C. All right, so let's try this out. What if we had a number, I'm going to make it up again. Here's our binary number. You start from grouping from the right. By the way, the most right digit is called the LSB, which means least significant bit, and the most significant bit is on the left, MSB, most significant. All right, so we're going to group starting from the least significant bit into groups of 4. All right, so this one we have a 1101. If you look at our chart over here, 1101 is a D, so this is a D. 0101 is a 5. 1101 again is a D, and then you could fill in leading zeros. This is a 1. So we have 11101, 0101, 1101 in base 2 is equal to 1D, 5D in hexadecimal. Cool. So now we know how to convert from decimal to binary and then from binary to hexadecimal and octal. So let's go do some other fancy conversions. All right, let's try to go from octal to hexadecimal. So here's our problem. Let's try 241 in octal is what in hexadecimal? All right, so I think the easiest way to do this is to write it in binary and then convert from binary to hex. So we know that each octal digit is 3 binary digits, so your 2, your 4, and your 1. Now to get it into hexadecimal, we then group that binary into 4s. So we're going to get a 0, a, so that's 10, and a 1. So 241 base 8 is equal to A1 in base 16. Now just for kicks, let's also convert this into decimal. So this is going to equal, again, I'll write these place values here. It's going to be 128 plus 32 plus 1. So that's going to give us 128 plus 32 is 160 plus 1 equals 161 in base 10. Voila! So now you know how to convert all over the place.